gonna start it. All right, and then I usually double check to make sure because it should be live, but I like to double check. So hang tight. Because I'm like, I think I did this one time where I hit the wrong button. And I'm like, I started talking and people are like, I don't see anything happening. I'm like, oh, that's what
Classic.
I get for switching computers. So let me, ta-da. Okay. All right, let's see. Should be easier to do this. Anyway, okay, go. All right. Let me see. Okay, we are live. Just making sure. All right, so, anyway. Welcome, everybody, to our, well, for some of us, morning chit-chat, morning coffee chat. For others, like our friend Maxime. What time is it over there?
It's 6 p.m.
6 p.m. So it's a evening talk.
Yes.
But
Evening tea.
yeah, evening tea. So we are super excited to have him here today. Let's see. He's going to talk Aurora phenomena with us. You know, some of the IDing some of these things that we see. So Maxime Grandin holds a PhD from the University of Finland, or Oulu, right?
Oulu, yes.
Oulu,
Yes.
yeah. And University of Toulouse. I probably said that wrong too.
Yeah. No, that was perfect.
All
Toulouse, yeah,
right.
perfect.
And so your research interest covers magnetosphere-ionospheric couplings, and you've recently been working in auroral physics, leveraging citizen science, specifically with the Arctics project, which is auroral research coordination towards internationalized citizen science. I've been a fan of this project because there's been some really cool stuff to come out of it. So we are super excited to have you here. I know we're gonna learn some things, so I'm thrilled to just hand it over to you, and you can roll right into what you got to talk, and I will
Thank
shut
you
up.
very, very much. Yeah,
Yeah.
no worries. Thank you very, very much. Let me share my screen so that you see the slides. So if I said it was F5, right?
Yeah.
Yep. So I think now you should see the slides in full screen, and I'm going to start. So, well, first of all, as I was saying, thank you very much for inviting me to take part in the Space Weather Unplugged live stream. I mean, it's really a pleasure and an honor to be here. And I hope indeed that you will get something out of it. I tend to be chatty, so I'll try to stick to the allotted time. And if not, just rush me. I will speed up because it's good if we can have a bit of time at the end for some questions, some discussion. I would love those interactions. Okay, so very quickly, I was thinking I could just show on a map the important places, or at least those that are really dear to my heart. So I'm, as my name betrays, I'm originally French. I grew up in Rennes. Rennes is located in Brittany, so that's northwestern France. But then for university, I ended up in Toulouse. I did my undergrads there. I actually did an engineering degree in space engineering. And then my journey in Finland started in 2013. I moved all the way to Sodankylä, which happens to be right within the Auroral oval. And there I started my PhD in ionospheric physics as a double degree. So the universities were Oulu and Toulouse, as Mary Beth said. During my time in Sodankylä, I had the privilege to spend a few months even further north on Svalbard. So here we are on the poleward edge of the Auroral oval typically. There is a university center there, and I got to study for a few months. It was really, really an interesting place, and I could see dayside aurora, for instance, over there. For the past 8 years, I've lived very far south in Helsinki. You can't get much more south than that in Finland. So first I was a postdoc at the University of Helsinki, and for the last year I've been a researcher at the Finnish Meteorological Institute. So today I will touch upon 4 topics. I was thinking to first maybe give a relatively brief overview of the processes that start at the sun, but then ultimately lead to the formation of the aurora. I'll try to skim through it quite quickly so that we have time for the rest. And I suspect that most of you already have some quite solid background on the topic, but just to make sure everyone's on the same page, I'll go through that. And then I will talk about the citizen science project, especially Arctics, because I think, yeah, I want to advertise a few things we've been doing, and I think, yeah, it's something that should be interesting for your community. Then I've been asked to glance through a few oral forms that you see down your latitudes when there are like big storms. So I've picked a few of them and I'll very briefly give some facts about them and we can maybe discuss them more. Mind that disclaimer, I'm not an expert on all of them. So when I don't know, I will just honestly say I don't know. But you can find more information, of course, on the material that I link. And then I want to end today with like a request actually to the community, because as you know, citizen science could not happen without the citizen scientists. So I want to give you some tips on how concretely your pictures, for instance, your observations can help us researchers to do beautiful auroral research. But yeah, let's start with a quick journey from the sun all the way to the upper atmosphere. So space physics, just to give an overview, space physics is essentially the study of the interactions between three entities. You have the sun and its expanding atmosphere, the solar wind. You have the magnetosphere, which is the magnetic bubble around the Earth. And you have the atmosphere and its ionized part, called the ionosphere. And essentially we study the interactions between those three regions, and we do that based on observations that can be from satellites or from ground-based instruments, and also a lot of code like numerical models. This is essentially what we do on our day-to-day work. We don't spend that much time actually watching the aurora, unfortunately. So the sun, as you know, it's the star of our solar system. I'm not a solar physicist myself, but you can see here a sketch explaining that the sun consists of several regions. It has a core where you have those fusion reactions that happen between hydrogen atoms to produce helium. Then the energy is transferred towards the outer edge of the sun, first via radiation and then via convection. And on the surface, which is the part that you get to see, you can have some interesting regions, such as sunspots, for instance, or coronal holes that you start seeing in some solar imagery. And what we call the corona is the visible atmosphere of the sun, where you can really see structures which are betraying the direction of the magnetic field coming out of the sun. So here you have like pretty images from some satellites observing the sun. The sun's expanding atmosphere, so it's a plasma, it's a mix of essentially protons and electrons. It's what we call the solar wind. And because the sun is not a solid body like the Earth is, it has a rotation that we call differential. That is, you have to imagine the sun is this kind of bubble of plasma, or like very hot gas, meaning that the equator latitudes of the sun tend to rotate faster than the polar regions of the sun. But overall, if you average the rotation period across all latitudes, you find a period of about 27 days, which is why, as you probably noticed, when there is a very big storm, chances are quite high that approximately 27 days later, you might have again some big disturbance, because very often it means that the same region at the sun is now reappearing in front of the Earth, and it might unleash another CME or some high-speed stream. Yeah, I'm not going to talk much more about the solar wind. Here you have visualizations of what solar flares are, these flashes of light here. So we are especially looking in the X-rays, so like very energetic photons here. And associated with solar flares, quite often you have coronal mass ejections, which means that some solar material is actually released. So we are talking about hot plasma, protons, electrons, and when these CMEs are directed towards the Earth, they may lead to a beautiful auroral show after, like, say, a couple of days on average. Now let's go back to the Earth. To get aurora, we need an atmosphere, and thankfully, the Earth does have an atmosphere. Our neutral atmosphere is divided into 4 regions, and the division is based on the temperature profile. So in the lowermost part, for the first about 10 kilometers, we have the troposphere, which is where the weather is happening, like the real weather, not the space weather. Then you have the stratosphere, where you have especially the ozone layer, the mesosphere, where the temperature gets quite cold, and then the top part of the atmosphere is called the thermosphere. Again, I'm not going to go in great details on that, but one important thing is that above approximately 100 kilometers, you have atomic oxygen, which you do not find on the surface, right? It's molecular oxygen, O2, that we have, that we breathe. But about 100 kilometers altitude, you start forming atomic oxygen, and it's important because, as you will see, this is a species which produces auroral light. Okay, well, now from the background atmosphere, you have ultraviolet radiation and X-rays coming from the sun, solar light. They in the upper atmosphere, those rays can ionize the molecules and the neutral atoms, and this is why you start having some free electrons and some ions in the upper atmosphere, and this is the layer that all the component of the atmosphere that we call the ionosphere. The ionosphere is typically divided into 3 regions, D, E, and F, and essentially the aurora takes place predominantly in the E region and a little bit in the F region as well. Now, as I mentioned, there is a third entity which is important for space physicists. It's the magnetosphere. And the magnetosphere forms because the Earth has an intrinsic magnetic dipole due to the metal that is flowing in the core of the planet. It creates a magnetic field that if the Earth was in just complete empty space without the sun nearby, this magnetic dipole would look somewhat like this. However, the Earth and its magnetic field happens to be in the vicinity of the sun, where there is the solar wind. So when the solar wind is flowing, it will actually compress the magnetic field of the Earth on the day side and stretch it very, very far on the night side, forming what we call the magnetotail. So this gives rise to the magnetosphere. So the magnetosphere is essentially the magnetic bubble within which the Earth is located, and it is delimited by a region we call the magnetopause, and you can see it has this shape with like compressed day side, so the solar wind here is coming from the left, and very, very stretched night side. Ahead of the magnetopause, you also have a bow shock, because the solar wind propagates at a speed which is faster than the speed of the waves that can propagate within it, meaning that it is brutally slowed down when it's encountering the obstacle formed by the magnetosphere. So it creates a bow shock. Again, I have written more than I will actually say on those slides because I don't want to waste too much time on this. What is important to know is that magnetosphere and ionosphere actually form a very strongly coupled system. And this is thanks to those couplings that we have the aurora and other space weather phenomena. This picture looks horrible, because there are so many arrows and things happening. Yes, it is a bit overwhelming for researchers too, if I'm fully honest. But essentially, among the ways a magnetosphere and ionosphere are coupled, you have some currents flowing from the magnetosphere into the ionosphere, along the magnetic field lines, for instance. You have some ions from the topside ionosphere which escape and start populating the inner magnetosphere, and they will modify the properties of the plasma there. But more interestingly for us, you have protons and electrons from the magnetosphere that can precipitate into the ionosphere. That means they follow magnetic field lines and they end up in regions like around the poles. They enter the upper atmosphere and ionosphere, in regions that we call the auroral ovals. So here you have a movie that you perhaps have already seen, which explains how from the solar wind things are coupled from the solar wind to the magnetosphere and to the ionosphere. So on the day side, when the solar wind has when the magnetic field of the solar wind has the suitable orientation, you can have a process called magnetic reconnection, which opens magnetic field lines from the magnetosphere. And then when on the night side those field lines close again, the particles that were, like the charged particles, so electrons and protons that were on those, they end up precipitating in the auroral ovals, as you can see here. And there are two ovals, one in the northern hemisphere and one in the southern hemisphere. Let's get to the real business, the aurora. So when those particles approach the upper atmosphere, at some point, the density of the atmosphere becomes high enough for the likelihood of a precipitating electrons to meet an atmospheric constituent to become actually quite large. And when this happens, there is a collision between the precipitating electron and the atmospheric constituent. Let's say it's an oxygen atom, for instance. Then when this happens, one process that, some energy is transferred from the precipitating electron to the atomic oxygen. This atomic oxygen can become in a state that we call excited, meaning that it has a bit too much energy stored within it, and it's not meant to last forever. Excited states are not stable. So how to get rid of that excess energy? There are several ways. If very shortly the excited oxygen happens to hit another constituent, it can then lose this excitation and then nothing else happen. But if not, then it will have to emit a photon. A photon is a kind of grain of light, and it's basically pure energy. So this excess energy that the oxygen atom had because of the precipitating electron is now released in the form of light. And when you have many oxygen atoms releasing photons, you end up having patterns that look very much like the aurora, and that actually happen to be the aurora. You see and you have seen in the field for sure that the aurora can have several colors. The colors depend on the excited species and also the level on which they are excited. Oxygen, for instance, atomic oxygen can produce red emission or green emission, typically. Whereas if you see blue, it generally comes from the N2 plus ion, so molecular nitrogen ion. And this is only the part that we can see with our limited eyes, but there is also aurora produced in infrared and ultraviolet, but sadly we cannot see that. So you're probably also familiar with the concept of a substorm. So a substorm is essentially a big auroral event. It corresponds to some dramatic reconfiguration of the magnetic field in the magnetotail. So you have massive reconnection happening in the tail, and it unleashes lots of charged particles that precipitate in the auroral oval, and there are beautiful auroral displays. So this is really the time when you want to be outside. And a substorm is divided into several phases, and during each phase you will have a different type of aurora. An auroral substorm starts with the growth phase, and during this phase typically you have one or several pretty clear arcs that are typically in the east-west direction that appear relatively quiet. They are not necessarily extremely bright, but gradually those arcs start drifting towards the equator. So if you're in the northern hemisphere, they will be drifting towards the south. And when the growth phase ends, you start having what is known as the breakup, which is followed by the expansion phase. So the main growth phase arc at some point will start becoming brighter. It starts activating, it starts exhibiting maybe some irregularities, some dynamical features. So that's the breakup. And then the expansion phase, during the expansion phase, the aurora starts rushing back towards the north if you're in the northern hemisphere, and having crazy displays, forming complex structures, like you can have spirals and so on. You can have like beautiful displays such as the corona, which is a perspective effect when the aurora is just above your head in terms of like magnetic direction, like just aligned with the magnetic field compared to you. This is the beautiful expansion phase, which lasts for sometimes a few minutes, sometimes a couple tens of minutes, depending. But this is the moment of the show you really don't want to miss. After that, things get a little bit more quiet, or at least in appearance, it looks like much dimmer. But you start having a process that is called pulsating aurora, in which you have patches. So this is a bit faster than reality, but typically you see like you can have several kinds of pulsating aurora, but one example here is like what is known as patchy pulsating aurora, where you can identify some patches which are going on and off and on and off. Typically, there would be like, say, 5 seconds on, 5 seconds off, 5 seconds on, 5 seconds off. And this will cover pretty much all the sky above you. It will be quite dim. So you need to kind of really pay attention to see those structures, but it's actually pretty cool when you notice it, I think. But doesn't make as spectacular pictures. Okay, that was for the quick overview of how do we get Aurora. Then I want to talk to you a little bit about what we have done with the Arctics Working Group in terms of citizen science. So Arctics, so yeah, it stands for Auroral Research Coordination towards Internationalized Citizen Science, and it started as like a collection of both professional and citizen scientists, essentially from Europe and North America, that submitted a proposal to the International Space Science Institute in Bern to get sponsored to a couple of times have a 1 week meeting in Bern to talk about how we can, go further in terms of citizen science to study process phenomena like Steve, for instance, or the June aurora, and I'm going to talk about those in a minute. The proposal got selected, so we could have, actually, I should have updated this slide. Now we've had the third in-person meeting also in May this year. So we had 3 1-week meetings, like the 15 of us who are in this working group. But the aim of Arctics is to be as open as possible to external collaborators. And we have over 20 very active external collaborators. Some are citizen scientists, some are from the academic world. And they come from, I think we can be proud saying that we actually managed to reach communities across multiple countries. We have Australians, we have Belgians, Canadians, people from the UK, so England and Scotland. Note that I'm Breton, so I separate them, make sure to not wrong anyone. We have Japanese collaborators, we have Dutch collaborators, people from New Zealand, very active community in New Zealand, Sweden, and the US, of course. And essentially, we've had roughly monthly meetings. Now it's been a few months without a meeting, actually. But the idea is that we want together to really do as much as we can investigations of strange auroral forms, processes where we actually have more questions than answers. And we believe that citizen science imagery can be extremely valuable for that. So yeah, we've really striven to keep the door open to welcome more people who want to collaborate, either on the citizen science side or on the academic side, because yeah, we want to share the fun with others. Among the outputs of Arctics, I believe you probably have heard of the Field Guide and Handbook for Citizen Science that got released approximately a year ago already. That was a work under the lead of Katie Hurlingshaw from Svalbard, where especially several citizen scientists have been extremely active. I will name at least Donna Laak from Canada, Marian Spijkers from the Netherlands, Emma Bruus and Eero Karvinen from Finland, and I will stop here. because otherwise I will feel like I should give the complete list and I will piss off some people. But but essentially those documents, you have the link here, you have the QR code. They are free. They are completely accessible. Feel free to use them, share them, and let us know also if you have any feedback, because we are currently working on some update for it. After 1 year, we feel that we've learned new things and we have ideas on things to add. But so yeah, if you have any feedback, we are really happy to hear suggestions. Another output from Arctics, or like adjacent to Arctics, is a review paper on citizen science in atmosphere and space physics. That actually came as the output of a workshop organized by EC on atmosphere and space science and the links between the two. I was a participant there, and I presented what had been done on citizen science, at least from the Auroral community, and together with quite a bunch of people, as you can see here, we produced a review paper, and it's open access, so feel free to have a look at it if you're interested. It doesn't cover just the aurora. It goes also, includes also like atmospheric physics, solar physics, and so on. But and it cannot claim to include absolutely every single project within those fields, but we tried to give a good overview of what's going on, what has been done, which directions we could go to in future. So yeah. Another output of Arctics on which I can say a few words is a survey of the auroral observations that took place during the May 2024 storm. Some of you might have come across the survey that we shared shortly after the storm happened. Here you have a map of the observations that were reported. So every black dot or blue triangle corresponds to a person who answered the survey saying that, yeah, I have seen the aurora from that place during the storm. So this resulted in a publication that was published in Geoscience Communication almost a year ago, actually, and it's also open access. I've been told by several people that it's easy to read, so you don't need to be a hardcore scientist to follow. So if you're interested, yeah, definitely check it out. Among the results that we showed, we had a look at the local time and magnetic latitude where the observations came from. So this figure, actually, it's a way that we commonly use in space physics to display things above the polar region. So imagine you have the North Pole here, and you are seeing the Earth from above. So North Pole, and then as you go further away from the origin, you are getting closer to the equator. The numbers here are the geomagnetic latitudes. And here in this visualization, we put noon on top. So the sun is in this direction here. And then it means we have midnight here, morning is on this side, and evening is on this side. So what you see from this figure is that most of the reports came from people who saw the aurora in the evening sector between, say, 6 p.m. and midnight. And it's actually not so surprising, because people tend to watch the aurora before they go to bed rather than set the alarm clock at 2 a.m. to see the aurora. It's quite this doesn't mean that there was no aurora in the morning sector. It means that people were awake in the evening predominantly. We also asked in that survey what colors people had seen with their own eyes, and what colors appear in their pictures if they have any pictures. And we sorted that as a function of geomagnetic latitude. So you see that a lot of people actually saw some red, some pink, some purple. Many people saw some green, and a few could even see the blue with naked eye. And on pictures, it's even more present, the blue. The blue is difficult to see to the naked eye, to be honest. So yeah, essentially, what came out of this study is that people down to 30 degrees magnetic latitude could see the aurora at certain points during that storm. So it was really a crazy storm. And the fact that there is a lot of reports saying that they could see red and pink with the naked eye means that in practice, among the electrons precipitating from the magnetosphere, quite a lot of them had a low energy, meaning that they deposit their energy in the upper part of the ionosphere, and they produce red emission. And if the atmosphere happens to be still sunlit at those altitudes, this also produces blue emission, which appears as pink in those circumstances. So that was a very interesting result. However, we also noticed that, yeah, collecting data via a survey is a bit tricky. There are many challenges. Of course, we have to believe what people say. That's we base it on trust, of course. But the fact that we did not request the pictures means that it's a bit limited how much more we can interpret. So we have to go further and stay there until part 4 of the talk. And yeah. Also, I can tell that no matter how much you constrain the format of the responses to the survey, there will always be a lot of manual labor to reformat things, check for possible mistakes. So it's time consuming. But it's still, I think it's still a pretty cool paper. And yes, so with Arctics, the work continues, of course. And currently there are several studies which focus on specific emissions, and this is just a few examples of those intriguing forms that are the object of Arctic's studies at the moment. And this is a transition towards a quick review of some of the intriguing auroral forms that we don't know everything about yet. I mean, can we claim that we know everything about any form? That's a bit debatable, but some of the most mysterious ones. First of all, the very famous Steve. So Steve, I guess many of you have seen it, perhaps even photographed it. Sadly, I haven't. I was too high in latitude when I was under the Aurora, so I never, and Steve was not discovered yet. Maybe that also made it a bit complicated to see it. But essentially, Steve appears generally as a long and relatively thin arc or a ribbon. In terms of colors, we are more in the white or mauve colors. It is visible to the naked eye, and the orientation is predominantly east-west. Steve is intrinsically what we call a subauroral phenomenon, meaning that it happens equatorwards from the auroral oval. So not above Sodancula very often, to be honest. Yeah. Steve can be long-lasting. It can stay up in the sky for up to 1 hour, according to some observations. And I was attending the Steve workshop, which was organized in Alaska just last week. And I was very interested in hearing what's the ongoing research talking about for Steve. And now one aspect that really struck me was that several researchers and citizen scientists were talking about the fact that Steve is not that static, actually. If you manage to have pictures of Steve at a high enough cadence, you can see some structures, some dynamical features that are typically smoothed out when you have to take a maybe 10, 15, 20-second exposure. So there is a lot of research happening at the moment on Steve, and this is, I think, a pristine example of successful collaboration between academics and citizen scientists. So on each of those slides, by the way, I include selected publications on the topic. They are scientific publications, so maybe not as accessible to well, non-academics, but they might be worth a read, and I'm sure that you can actually extract quite a lot of information from them if you want. I'm not sure if all of them are open access. I hope they are, but if not, we can always you can always email the first author saying, could I please read your paper? And they will be very happy to hear that someone wants to read their paper, and they will send you the PDF. They're allowed to do that. Okay, when we talk about Steve, very often, right after that, we start talking about the picket fins. The picket fence is, well, you have a very beautiful picture by John Anderson here showing what the picket fence is. So you recognize, Steve, here. The picket fence is those green structures which form, well, something that looks like a picket fence. Those structures are green, they are visible to the naked eye, and as you can see, there is some form of periodicity in the way they are laid out. At the bottom or at the foot of those picket fence structures, which, oh yeah, I forgot to say, they are aligned with the magnetic field direction. At their foot, sometimes, not always, and maybe I'm not sure how often in practice, but you can have very, very tiny green blobs, which have been called streaks, and they are very tiny. Here we are talking about a scale on the order of 1 kilometer. And those, as far as I know, it's not yet fully clear what these are, the streaks, the picket fence, what creates the emission mechanism. Well, the same can be said for Steve, actually. It's still heavily investigated what is the exact mechanism for getting the emission in Steve. So, but why do they sometimes appear along with Steve? Why not always? This is still a little bit of a mystery, and hopefully in the next few years there will be more papers coming out giving some answers. Then we were talking about the streaks, which are seen together with the picket fence. So with Steve, so subauroral. Well, there are some very similar looking structures that have been called fragments or fragmented auroral-like emissions, or phase for short. Same characteristic size, so on the order of 1 kilometer, same color, they are green. The fragments, they have, however, been originally found on Svalbard, so very high latitudes, poleward side of the auroral oval. They can be semi-long lasting. Well, they are not like just flashes. They can stay up for a few seconds, is quite common. I think I've read that up to a few minutes they can be visible, but they tend to be quite dynamical in like they will come, well, occasionally isolated, but often in small groups like this, and they will have they can have some drifting motion. They can have maybe some brightening sometimes. They are visible to the naked eye. They are, if the aurora is bright, they will be more or less equally bright, so you can spot them to the naked eye. But yeah, as I was saying, they were seen from Svalbard initially, but they are, now that people are getting aware of them and looking for them in their footage and so on, they start also being seen elsewhere within the oval. So, but what creates them? Big mystery, honestly. This is really like ongoing research. Then I come to maybe my favorite one, which is the Dune Aurora. So the Dune Aurora, I very much like this picture by Graham Whipps, who is a photographer from Scotland. You have this diffuse green aurora. We are generally on the equatorward side of the auroral oval again. But here, the diffuse green aurora shows some very intriguing structuring in the form of horizontal waves. And they have been discovered, the dunes have been discovered by Finnish citizen scientists, and they've been called like that because of their visual aspect. The person who gave the name is a Finnish photographer. Her name is Pirjo Koski, and yeah, she came up with the name of the dunes. So the dunes are generally very faint. I have never seen them myself, sadly, but according to those who have, especially those who have experience, they claim that if you know they are there, you can distinguish them. But generally, you will see them on your pictures, and then by squinting a lot, knowing that they should be there, you might see something. But don't expect it to be like a very bright display. The dunes can stay up for several hours. Well, from a given location, up to a couple of hours, but dune events can really extend across many local times. like in the paper that I wrote a few years ago on the dunes, from based on the event, which is photographed here. The dunes were up for like more than 4 hours. They were first seen in Finland, and then as time was going by, they started being seen in Norway and Scotland, so covering like really a lot of local times. It's typically an evening time phenomenon, and yes, they can have a slow drifting motion. If you have a time lapse, it's pretty clear that they tend to drift. But again, the dunes, what are they? We have some ideas, but still ideas. Like there is no final answer to that question, so still very much ongoing research. Then SAR arcs. So SAR stands for Stable Auroral Red Arc. It's a diffuse arc. As the name tells, it's red. Usually you will not be able to see that to the naked eye. You will only see that on your pictures. It's again a subauroral phenomenon, so it's equatorwards from the auroral oval. On this picture, equatorwards means north from the auroral oval because this is a picture from New Zealand. So we're in the southern hemisphere. Les Ladbrokes has amazing shots of multiple phenomena. And you can tell that it's from the southern hemisphere because there is one of the Magellanic clouds that is very prominent here. We don't see that from the northern hemisphere, sadly. So the SAR arc is oriented in the east-west direction. It's very elongated, and it's relatively broad across latitudes, like broader than Steve, for instance. And it can be up for like several hours. It's quite stable, and it should not have structuring like rays. If you start seeing rays, it hints at particle precipitation, so it hints at aurora. SAR arc generally is very diffuse. SAR arcs have been known for quite a while. Like I think there are some publications in the 70s reporting SAR arcs, but as far as I've understood, their exact formation mechanism, what they actually are, is still a little bit debated, and there is quite a lot of research going on, especially the Martinez et al. Paper from just a few years ago investigated the relation between SAR arc and Steve. Sometimes it seems that Steve can become a SAR arc and vice versa. Why does that happen? Is it really so, or is it just going? It's still a lot of open questions. Then, okay, it's a bit still early morning for beer, but we can talk about IPA, isolated proton aurora. So this is on this picture that's taken by Eero Karvinen from Finland. It's this blob here. You have the main auroral display here. So the north is on the left, the south is on the right. And here, equatorward from the main aurora, you have this quite diffuse blob, light green. It's faint. I'm not so sure how much you see it with the naked eye, probably same as the dunes. And this blob can appear and disappear and reappear again. So we are not talking about pulsating aurora in the same way as you have during the recovery phase of the substorm, but it does have some behavior that evokes some sort of pulsation. And it has been found that isolated proton aurora is very often related to electromagnetic waves called EMIC waves that happen to live in the inner magnetosphere, especially in the evening sector. And they produce proton precipitation because they can interact with the protons that are trapped in the inner magnetosphere and kick them into the auroral oval. And then when the protons precipitate, they can have those optical signatures as those isolated proton auroras. And then still related to protons, there is RAGDA. RAGDA stands for red and green diffuse aurora, and it's diffuse green structures, like here that would be this arc, that have also some red emission above. They are described in a recent paper by Toshi Nishimura, in which citizen scientists were involved, like Eero Karvinen was involved, for instance, and a few others. Ragda is very faint, so I'm not sure how much you can see to the naked eye. I would guess that the red, you don't see it. You might, squinting enough, be able to see the green. It's again a subauroral phenomenon. And in Toshi's paper, they found that these emissions come from atomic oxygen, red and green, makes sense, but excited not by electrons directly precipitating from the magnetosphere, but what we call secondary electrons coming from proton precipitation, meaning that the particles coming from the magnetosphere are protons, but as they enter the upper atmosphere, they can interact with the neutral species, and this will lead to the formation of electrons which propagate downward as well. Like they will essentially kick electrons out of some atoms, for instance, and these electrons, when they hit atmospheric constituents, they will excite the oxygen and produce some red and green. So that's RACTA. And another one, another type of aurora, which has come into the spotlight only very recently, it's the continuum aurora. So continuum aurora appears as white/mauve/gray structures, depending on the circumstances. It can appear as rays, like on this picture from Marian Spijkers. That's a picture taken from Svalbard. But it can also be seen in more dynamical auroral forms. Like when you have, for instance, very strong substorm activity, sometimes you have areas which are not green, are not red, are not pink, but they are actually a mix of many things. And if you decompose the light to look at the spectrum of your emission, you see that you do have spikes in the green, in the red, and so on, but you also have the whole wave, like a very broad wavelength that are excited, that are present in the emission, and that is what we call the continuum. Continuum aurora has been seen in many places, actually. There is no one location where to look for it. Many different local times on Svalbard, they have it also during daytime occasionally. The paper by Nora Bartamies et al. Reviews this continuum aurora from Svalbard, and they see it in many, many local times. So very intriguing, very new. Stay tuned. Okay, I am more or less up with my official time, so I'll try to be quite quick, but this part should be relatively quick. So as I said, I've insisted quite a lot on the fact that a lot of the research is ongoing, many questions, many answers to be found. How can you help? Well, the best way you can help us is to share your observations and report them. There are essentially, as far as I'm aware, two main platforms on which you can report your observations. There is Aurorasaurus, that I am sure you're all very familiar with, and I am certainly not the best person to talk about it. So I assume that you know what Aurorasaurus is and you know whom to ask if you want more info. But I'm going to talk a little bit more about Skywarden, because that's the Finnish thing,
Yeah.
and maybe a bit less known to the US community. So Skywarden, in Finnish, Taivaanvahti, it means basically essentially the same except in Finnish. It's an observation database that is maintained by the Finnish Astronomical Association, which is called URSA. And here I give you the contact of two key people from URSA. In case you have any question when submitting your reports, email Emma Bruce or Eero Karvinen. There are certainly others, but those two are those I'm comfortable sharing their email address. And I know that they will be very happy to assist you, and very, very excited to get more observations from North America. So very quickly, I'm going to tell you how it looks like so that you're familiar with it. So to report an observation, you have like two ways to go there. Either you go to this drop-down menu and report an aurora, or on the right-hand side sidebar, you have also a direct link. And if you click on this, it looks like this. You first have like a map. The map actually by default is centered above Finland, over Finland, so you can just zoom it out. The rest of the world does exist beyond Finland. Essentially, it will look like this, and there are very important points. And the most important of all, I will say, is when you fill in the time. So you put in the date of your observation and the time. For the time, I'm talking to North American people, so I have to emphasize use the 24-hour format, because otherwise, if you put 9:30, it will assume it's 9:30 a.m. And then the conversion to UT and everything will be messed up, and people will be, well, I think there might be a 12-hour offset. So yeah, I cannot emphasize too much that, yeah, in the date and time, at the time especially, make sure to put the 24-hour format. The date is day, month, year, as per the European standards. Also, that's another one to pay attention to. Then to determine the observation location, you can just zoom on your area and just click on the map, and it will save the locations where you took the pictures. And then it is necessary to put your real name and email address. That's in case the moderators need to contact you. But if you don't want your name to appear publicly, you have a box that you can tick to say that, or that you can untick to say that you wish to remain anonymous. Mm-hmm. Then if you scroll down, you get to the part where you describe your observation. So you have first on the left side a drop-down menu where you select the type of aurora. It's quite self-explanatory. Some question about how bright the aurora was, and that last question, are you a member of an astronomical association or a team? For most people outside of Finland, this will not be relevant, but I think the Alberta chasers have been added. So do have a look if you belong to a group. And if you want your group to be added, I'm sure you ask Emma or Eero and they can do something about it. But it's not crucial. Then you have a free text box where you can describe in your own words what you have seen. It's not mandatory, but I would recommend writing a few lines, and you can write in English. It will be automatically translated into Finnish and Swedish by the system. Just write in English. No need to learn Finnish for that. What is particularly interesting for us scientists, if you can indicate that, for instance, if you have seen the dunes, it's very interesting for us to know if you can mention, like, the dunes are present on my pictures from 9:28 p.m. till 9:46. Even if, like on the previous one, you might have said that the whole time span during which you took pictures was from 8 p.m. to 11 p.m., right? Here you can give more details in this box and say that the dunes are present from 9:37 to 9:46, and then that can be very useful in the future. And then, very important, I recommend uploading at least one photo. It's not mandatory, but it's good practice, especially if you have captured some intriguing forms. If you have like 1,000 pictures of that night, and there are only, I think, 8 that you can add, but you can actually put them into a video and also upload a video that's supported. And for more technical details, ask Emma or Eero. And then I invite you to click. There is a button a bit hidden here that says more information. I invite you to click on it because then you can identify the auroral forms you've seen. So if you click on it, then it opens this part, which will appear below the previous screen. And additional information, especially what's interesting is if you know some auroral forms that you've seen. For instance, I've seen a Steve arc, I've seen a picket fence, I've seen the dunes. You can tick those boxes. If you're not sure, you can still tick that, and it will be anyway reviewed by a moderator. So if you've identified something, but the moderator thinks that, oh, actually, no, it's not that, no worries, they will take care of that. So don't be afraid. Then if you want to give technical info about like your camera settings and so on, there is a box for that. There is also a list of specific features and colors that you could see with the naked eye. If you want, you can put that. And most importantly, don't forget to click send. Okay, and I think that's it. So yeah, I've gone like maybe 6 minutes extra compared to the original 45 minutes, but we still have time for discussion, questions. So I'm very happy to take that now, and I hope you enjoyed. Thank you.
Yes, thank you. I know, I always like to, I had my mic off the whole time because a lot of times I like to put little comments in there because it's like it's kind of fun to chit chat while it's going. But a couple of the comments we had, SAR arcs, I think the more energetic something is, that can make that a little bit stronger. Because there have been times, specifically last October, where it was quite naked eye visible, like from northern
Okay.
Michigan. But that particular week had a lot going on, so it's like it just never had a chance to calm down, so to speak. So is that a possibility in that realm?
So I'm not an expert of SAR arcs, but as far as I know, they are thought to be related to processes happening in the ring current.
Mm-hmm.
So from my non-expert perspective, an educated guess would be that it does make sense maybe to have like brighter SAR arcs if the geomagnetic activity has been going on and on for a long
Right.
time,
Yeah.
because probably more energy is stored in the ring current. And again, I'm not knowledgeable enough to pinpoint what's the exact process that creates the SAR arc. It's not electron precipitation like the aurora. It's more like, yeah, related to ring current. But to me, it makes sense. And if you saw it with the naked eye, I believe you.
Yeah,
But
it
I,
was it was pretty. I've only
but
to your point, most of the time, even like the first time I've seen it, it was only visible in the camera. But then there were like these few times where like I'm like, wow, that's pretty apparent.
actually, and that brings a question to me. When you see it with the naked eye, can you even tell that it's red, or is it this kind of
It's
grayish?
to me it's grayish.
Right.
It
Yeah.
just kind
I
of
guess.
is
Yeah.
fuzzy and it goes. The telltale sign for me is that it goes across the Milky Way, because that means it's pretty far
Right.
removed from the main band. I'm
Right.
sure some people can see color in it. I'm one of those people that can't see color that well at night, so most of the stuff is kind of
Mm.
grayish to me anyway.
Yeah. I
Um,
mean, it depends on which sensors are
right.
excited in the eye, right? So yeah, yeah. If it's only the sticks, it's gonna look gray.
Yeah. So, but I still think it's cool. Um,
Mm.
I'm trying to think. Let's see. Yeah, Janelle says it was red, so she could see the red in it. So
Wow.
lucky
That
her.
must be impressive.
Yeah. And then I had another question, because it had to do with the proton um, aurora and maybe Ragda, because I clearly remember it caught me off guard. This is probably 2 years ago now, and I was in Minnesota, and it started to get dark, and there was like this really bright light that came up over the trees, and it was very blobby and weird looking. But when I took a picture, it was bright green and red, and so I'm thinking that was the more. I don't know if it was proton or Ragda or maybe both.
This sounds like, well, Ragda is related to proton precipitation,
Okay,
right? So to
yeah.
me, that sounds, what you described sounds like Ragda.
Oh,
Yeah.
yeah, and it didn't last too long, but I
Hmm.
noticed it was like right when something hit, and the density in the solar wind was extremely high. Is there a correlation with that? Because I know that's kind of debated subject. Like, does density really drive some of these things versus other aspects of the solar wind, or is it a combination of a bunch of things?
So I can't give you an absolutely certain answer, but to me, it is reasonable to assume that it might be, because when you have an enhancement in a very sharp enhancement in the solar wind density or pressure,
Hmm.
so a pressure pulse in the solar wind, it kind of compresses the dayside magnetopause, and then because you're disturbing the magnetosphere, you can create all kinds of electromagnetic waves. And
Okay.
electromagnetic waves, maybe some of them happen to really activate the EMIC waves in
Hmm.
the, say, evening sector, and EMIC waves are known to drive proton precipitation, which then can produce those secondary electrons that produce the Rankine emission. So to me, I can't say for sure for that event if that was the case, but it doesn't sound unreasonable.
Sounds good.
This
That's
is a very scientist type of
yeah.
answer. I'm sorry.
No, it's all good. I think the one really good takeaway here is the timing, because that's something I didn't really think about until fairly recently. Was like how a lot of the proton stuff is always in that evening sector, and then now when I go back into my head and all the times I've ever seen it, it's always been in that sector. So that was kind of a cool
Yeah.
little takeaway there.
Yeah. So for protons, yeah, like a huge majority of the proton processes are in the evening, and that's related really to the fact that when you have reconnection in the magnetotail, the charged particles that are injected in the inner magnetosphere, they start drifting around the Earth, but electrons goes toward the morning
Hmm.
and protons go towards the evening. So that's why you have like more proton precipitation on the evening. However, there are I think SAMs, so that's sub auroral morning proton spots that are proton aurora spots that can be seen in the morning sector. I don't know much about those, I just know that they exist. So there can be some proton features also in the morning side, but that's not the most typical.
Yeah, that's really cool. And then I think I had. Let me see if I have one more question. Hold on.
I
I
think
think.
one comment that
Yeah.
we have is we have seen more proton aurora recently with some of the events, and I think one event in September was pretty spectacular. We
Hmm.
had proton aurora and Ragda showed up, so um, all of it was pretty much in the evening, but are there any specific conditions where we are more likely to see proton aurora? Because we don't see them with every single event.
Hmm.
Right.
That's a good question. Um, let me think if there is any obvious cause why proton aurora could be more frequent recently. I'm not sure. I'm not sure. Protons are often related to, yeah, EMIC wave activity. So if for some reason there are more EMIC waves that can drive more proton aurora. Also, if you have, yeah, I'm not sure. I'm not sure why. This is something
Yeah, I wonder
to
if it's
investigate. Yeah.
if it's more just timing. Like the one event, I think it's September 14th, somewhere around there. And I can actually get you some pictures from this because it was mostly a proton aurora party for us over here. But that coronal hole, I think we ended up getting, what was the CIR from it, where it was timed really well with us for the evening sector.
Mhm.
So I wonder if that was the triggering of it, was that we had all that initial compression versus like later on during the high speed stream where it just kind of, where it's just all the high speed stream instead. Maybe. I don't
It
Mhm.
was also
know.
well timed in the sense of the BZ going south and very, very sharply.
Hmm.
So we were starting essentially with very cold magnetosphere with not a lot of things happening, but the growth phase of that substorm was pretty intense because BZ was, I think, pushing minus 10 nanotesla or even lower, and that was a very sharp turn. So we ended up seeing giant undulations. We ended up seeing proton aurora. We saw Ragda. I think Steve was actually present in the recovery phase from that initial big substorm. So that was a auroral and subauroral party.
It really was.
We
Nice.
didn't we didn't get dunes. I haven't seen any picture of dunes from that time, but that was very intense. And that sharp turn into very deep negatives, that was very impressive. Density didn't change much. It was just BZ just literally dropping
Mm.
south all of a sudden.
Yeah, BC really drives the show.
Yeah.
Yeah. Yeah.
Yeah, it's really interesting, all these different, like you think you might have caught on to something and then it totally gets turned upside down again because they're like, well, that didn't match the last thing. So it's been interesting to, because when I first started this aurora chasing, it was always all about, well, first KP, which we quickly learned you don't want to follow that for chasing, but then it was all about BZ and BZ being south, but then you learn that that doesn't necessarily have to be the case. Like you get these sharp turns, like if you get a long extended BZ forever, then that actually kind of subdues things until you get like a sharp turn north or something to like kick it back.
Mm.
So it's like,
Yeah.
oh
Oh,
yeah,
you
there's a
end
lot
up
to
with a
this.
s- oh, you end up with a sawtooth event where you have beautiful substorms, but you have to wait for them for hours.
Yeah.
About 2 to 4 hours most of the time. Well, October 10th was a classic. It was very strong driving, but it was all BZ south for hours and hours and hours and hours. And we ended up pretty much saying, well, you have to wait. It will substorm eventually, but what you get is just kind of diffuse aurora that's doing something, but nothing that remarkable. And sitting right under auroral oval with intense negative BZs and just looking at the green soup overhead.
Yeah. So Janelle has this kind of goes from like we are talking about the timing, or like, how aurora changes across time, and it's so how much do auroral formations differ between viewing locations like at the same latitude, like the proton aurora that was in Michigan, and then was it, or like how would that differ if it would, like if you're at the same time but in Minnesota, which is a little bit further behind.
So between Michigan and
I
Minnesota,
think it's like
it's not that far away.
Yeah.
It's less than an hour in MLT, right?
Yeah, in UT,
in magnetic local time.
Yep.
Yeah. Yeah.
So it would have to be more of a spread then.
So I would think so, because those structures, they are quite okay. The fragments, the picket fence, they are very small
Yeah.
features, so you might not see them if you start moving like 500 kilometers away, like in longitude. You might not see like some fragments that are seen like, yeah, I'm not so sure about the actual distances between Minnesota and Michigan, but
Yeah.
it's what, a couple? Oh, and you're
Yeah,
talking
it's-
miles. Oh,
Yeah. It's not very far. In the grand scheme of things, it's not very far. Maybe like
right.
yeah, because
But so yeah, yeah. And so since the structures are very often in the east-west direction, if there is a Steve, say, can I be as bold as to say like that you would see from, say, Vermont,
hmm
then you might still see the Steve all the way to Minnesota, maybe.
Okay.
Because it's very elongated east-west, and it might be so that well, for the Vermont people, they have to look west, and the Minnesota people will have to look east, but they might be able to see the same Steve. And also, if we speak even about the SAR arcs, which are a bit higher up in altitude, like 400-kilometer altitude, then it means that you can have observers on the ground which are like having an even greater distance between them, but because the structure is higher up in the sky, they can still both see it. Do you know
Okay.
what I mean?
Yeah. So some of it has to do with the height of the
Yeah.
feature
The
as
higher
well.
the structure, the more you will be able to see it from afar, right?
Okay. That makes
So
sense. Because I
one
know
thing that
that's
I find, yeah.
because I think that's happened before, where some people, like you're saying, reporting sightings of like Steve or something way more east, and then by time it starts to move around, it's gone by then.
It can be, of course,
Yeah.
like between, say, mountain area and the East Coast, we start like talking about couple thousand
Yeah.
kilometers,
Oh, yeah.
right? Like a
Yeah.
1,000 mile or a couple thousand miles, right? So then it's a different story. But like for the states which are quite close to each other, I would expect that most of the time people would see more or less the same structures.
Okay. I guess she's asking. She's like, wonder about that Steve the other day. I wasn't even. I was at work down south, so I wasn't aware about the Steve the other day. But I mean, sometimes it just doesn't last that long either, right? Like, I mean, like you were saying, it can last for an hour, and I've seen it last a long time. But sometimes they're very fleeting. And
Yeah.
So I wonder if that's why. For her instance, is it just didn't last all that long.
One of the
It can,
events
yeah.
one of the events in April, I was able to see Steve. It was visible in the all sky camera, and it lasted about 20 minutes. And it was pretty localized, so you may not necessarily get it from your location, or by the time you are aware that Steve is there, because we do rely on reports of other observers, interesting features in the sky. By the time you turn around to actually catch it, because you're watching main aurora, it's not there anymore.
Yeah, is that, I mean, I can attest that too, because the September 14th event, I'm saying it's the 14th, it's somewhere around there. I didn't catch the Steve that everybody else did, because by time um, people were reporting it. I did a southward kind of just to check, and it wasn't there anymore. So my guess is they sometimes they just don't last all that long.
Yeah, one type of auroral form that is tricky to see, and that I can believe that people from different locations, even though in theory they should both
Mhm.
be able to see it, but they might actually not, is the dunes. For
Oh.
some reason, the dunes, I find them extremely difficult to see on all sky cameras.
Okay.
I've been looking at some all sky camera footage on specific events where Donalac from Manitoba has amazing pictures, and the University of Calgary in Canada has lots of all sky imagers. So I've been looking at the footage of that imager, and I know the dunes should be there. I just can't see them.
Huh.
And we've been really wrapping our heads around like why can it be so that you need to view them from a certain angle to be able to distinguish the variation in the luminosity. So elevation above the horizon probably plays a role.
Mhm.
If it's completely overhead, can you see them at all? Generally, all the dune pictures I've been looking at, they are taken at relatively low elevation, like typically looking in the east-west direction, and you can really see them going like that.
Mhm.
But I would be curious if someone happens to see dunes like on the left and on the right, can they also take pictures at zenith? Because if they are on the left and on the right of the observer, they are probably also overhead, right?
You would
But is
think,
it so
right? Yeah.
that pointing the camera, you just don't see it, you just have diffuse aurora, then it tells us that, okay, they are visible only with a certain viewing angle. And then
Mhm.
why? That maybe tells us something about their nature. How come we can not see them straight up overhead? Maybe this helps us understand a little bit better or constrain what are the possible hypotheses to explain that. So lots of, yeah, more questions than answers.
Right. Yeah, that's I think that's the one thing I've had to actually a lot of Aurora chasers have to get used to at this field is like you end up with more questions than answers, I think. A lot of
That,
times.
that if there was one take-home message from the whole Arctics thing, and that absolutely everyone shared that opinion, is that the more we dig and the more we find new things, the less we understand.
Right.
It's just so overwhelming. And I think that's something that must be super interesting from the chaser's perspective
Mhm.
is that you are really at the forefront of the discipline. The top scientists are clueless about the things that you are photographing, and I think that's super cool because it means, yeah, we can build tomorrow's science together. And the fact that you ask those questions, then it puts the scientists' eyes on those pictures and they're like, hey, wait, I actually have no clue. I have to look into that.
Right.
And that's really that's what I think is one of the very, very beautiful powers of citizen science, is that citizen scientists, they come with questions that professional scientists don't necessarily come up with because we have our assumptions, we have our prejudice based on what we know, and we don't think out of the box, you know. Citizen scientists, they are extremely knowledgeable, extremely skilled, and also extremely curious and not afraid of asking questions. And then those questions, generally, they are very good questions because we don't have the answers. So super cool.
It is neat. That's one of the things I didn't realize getting into this that, I was like, wow, this is we live in a world where you think that, instant gratification, there's answers to everything. And then you're like, no, apparently there's not. But it makes it
But that's the
super
beauty.
interesting. So,
Yeah, that's the beauty of science.
yeah.
Yeah.
So it's been fun to say the least. So I think because yeah, Janelle, yeah, if you can find them, definitely. She thinks she might have some Dune photos. So
Oh, please,
yeah.
please upload them to Skyward, and if you don't mind, because that would be like super interesting. I'm about to submit a paper in the next couple of weeks, in which I've been looking through all the Skyward and reports on Dune Aurora, and trying to start like getting some statistics
Hmm.
of where the dune appears and so on. And
Yes.
yeah, I have to thank those of you who passed on the message when I was asking for reporting events. And those of you who did report events, I know I really noticed that after the different communities advertised this call for events for June events on Skywarden, I saw a surge in the number of submissions from North America, from New Zealand, Australia, and I'm really, really grateful because yeah, that helps a lot actually.
So yay.
Thank you, everyone.
Yes, it's a I love this. I love the community effort of it. So I think let's see here. Yeah, do you have any more info about the picket fence? That formation seems like one of the most rare. Are you talking about the FAEs or the picket fence with Steve? So let's see if she says that. I think she might be talking about the FAEs because that's the one that seems like is the most
the very
rare.
small blobs,
Yeah.
right? The FAEs and their kind of cousins, which are seen at the foot of the picket fence, right? The streaks.
Yeah.
Yeah. So those ones, like, to be honest, I think there are no strong clues, or at least nothing published yet, about like what produces this emission. It has been suspected that, for instance, some internal instabilities in the ionosphere could maybe give rise to these emissions, but how exactly? I'm not sure anyone has the answer yet, but I know there is ongoing research to try to uncover those mechanisms. But what's particularly intriguing is their very small scale.
Yeah.
Like 1 kilometer in size. This is tiny. This is
Right.
really tiny. Yeah. And why do they come in groups? Or sometimes actually there's a lone wolf which just decides
just
to
one
pop
little.
up. Yeah. And why are they why do they last for like a few seconds? Why do some occasionally last for a couple of minutes? Why they appear there and not there when it looks like it's the same all over? But no, there must be some very specific and very localized conditions. It's very difficult to investigate this because they are short-lived. They are small, so on all sky images, they would you need to really look carefully to spot them. You do see them when you look, but they have been overlooked for a long time because they are not so prominent features. But then the problem is we don't have any in situ observations. You don't have, you can't fly a balloon. You can't expect a satellite to reach those altitudes. So it's really in this area where we have to rely on remote sensing. And even if you have a radar that's measuring those ionospheric radars, like you have at Poker Flat, for instance. So Pfizer it's called. Or you have several such radars, not that many, but you have some in Fennoscandia, you have several in the US. Those things, for them to appear exactly within the beam of the radar, that requires a lot of luck.
Yeah.
And even how can you be really sure that it is exactly in the beam? The only option to get in situ measurements would be to fly a rocket. Can you really hope to ever fly a rocket? Just throw them as they appear?
Yeah.
So it's very tricky. We have to be creative here and rely a lot on the theory also.
Yeah.
So getting back to the equations and so on, and I'm happy to leave that to other people.
Okay. And then she has a couple more. Are they always green or can they be pink? And then the other one is and sometimes it's like she's seen is there proton aurora fragments that can look like a picket fence but not exactly?
Okay, so on the first question, are they only green? As far as I know, so far they've been only green streaks or green fragments reported. Can they be pink? If they were found to also be pink, I guess that would be very interesting for the scientist community because then it would bring even more questions. But I assume that for now at least they have been seen as green. And then the possible role of proton aurora. My feeling is that it's highly unlikely that protons could produce these because when you have precipitating protons, inherently what you will get is some diffuse features. Just because the way protons precipitate, there are some sketches that I can try to draw up in the air. So imagine you have a proton which is precipitating along the magnetic field. Protons actually, they go down, but they also gyrate, right?
Mm-hmm.
And when they end up and steal an electron from some other species, they become a neutral hydrogen atom. And then they will not feel the magnetic field anymore, right? So they will just continue in straight line. But the direction of the straight line will depend on the gyro motion at the moment when it hits. So it might actually go like this until it collides with something else, loses its electron, and then it will again continue going down like this. What this means is that in practice, if you have a bunch of protons coming from above, they will become, the proton shower will become broader and broader as you go down, just because of this diffusion effect, this scattering effect, due to the fact that they occasionally become neutral, so they stop following the magnetic field, so they kind of spread out. And for this reason, the proton aurora is quite broad and diffuse. It's blobs, it's like broad arcs, very little structure can be seen. So if you see the picket fence, if you see the streaks, they are on the contrary very discrete features.
Mm-hmm.
So my guess is that they are not coming from proton precipitation because of that.
Okay. Oh, yeah.
Tomorrow I might be proven wrong.
Yeah.
But at least my educated guess is that.
I mean, that makes sense to me. It's like it's like, yeah, it happens like over a spread versus, straight. I told her, because she says she has a girl in a group chat that captured something pink and red. But I was like, yeah. She's like, maybe I'll just send it. I'm like, yeah, just send it. just send you the picture.
Sure. Yes. Yes.
Like, and if it's something really, you're like, hey, yeah, this is something different.
And if you send it, maybe put Katie Hurlingshaw from Svalbard in copy, because she's leading some fragment studies at the moment. So
Awesome.
She would probably have a better knowledge than me, or more up-to-date knowledge than I do.
Fantabulous. She says, thank you. Like, this is all so fascinating. It really is. Like,
Yeah.
Like, you never know what you catch out there. I think, well, that's one of the reasons I like it so much, is because no two Aurora shows are ever the same, like ever.
Yeah.
So it's like you always have
Absolutely.
something different, and
Yeah.
But yeah, I think
Yeah,
that
so that's what's so beautiful about it, because you can't predict what will happen
Right.
next. So every show keeps surprising you. Sometimes it's a bit of a bad surprise if it ends up like not being shown. It's very promising in the solar wind,
Yeah.
but then and then sunrise happens and then the show starts, but it's
Right.
not for you.
Yeah.
That's frustrating when it happens for the North Pacific.
Yes, yeah, we've all been there. So, but I think that covers most of the discussion. So
Yeah.
I can let you all
think
have your
so.
time back. Thank you so much for being here. It's been a wonderful discussion. I knew it was going to be cool. So thank you so much.
Thanks to you for inviting me, really. I mean, it was a pleasure, and don't hesitate to drop me an email. I can be slow at responding because the next few weeks are quite busy,
Yes.
but I will mark your message as, like, put it in red in my inbox, and at some point I will respond. And if I take too long, send me another email and I will respond.
Sounds good.
Apologies in advance for the delay.
All right, yeah.
Great.
So yeah, Steve and Janelle and everybody says thank you so much. So appreciate you being here, and I will let you all have your time back. And we'll just call it a day. So thank you so much. I appreciate
Thank
it.
you.
Thank you.
Have a great day ahead.
Yes.